Hello everyone. Am I audible?
Yes, sir.
Okay, so I welcome you all to the ninth week of this Gate Live session. So today I will finish complex analysis, whatever is left, and then I will move towards. I will also start Fourier series. Few problems on Fourier series will be solved, and then today I will be solving only questions like since I think the next week class your exam is on 11th, right?
Yes, sir.
Okay, so next week I will wrap up the Laplace and Fourier transforms. I'm thinking to do that. And today's class I will complete this so that you have your course is completed. So okay, I will start now. So in the last class we dealt with singularities and those kind of things. Cauchy residue theorem we already covered. So now we'll try to solve some contour integrals using this well-known Cauchy residue theorem. So as you all know that if a function fz is analytic, in a closed curve C, except at a finite number of poles or singularities which is within this closed curve C, then your contour integral fz dz is nothing but 2 pi I times sum of residues at poles within closed curve within closed curve C. So you just have to apply this formula to do this integral. So so there is a question which appeared in GATE 2017. This question is that they have to integrate this contour integral dz1 plus z square, and from minus infinity to infinity, and wait, I missed one question. Okay, first of all, let us solve this question. So this question came in GATE 2018, simple question. So you have been given some integral and you have to find its value, absolute value of this integral. And over this closed curve C, over this closed curve circle, which is centered at 1.5, that is 3.2, its radius is 1, so 5 by 2 and 3 by 2 minus, so 1 by 2. So this is your closed curve C, and you have to find this integral along this curve. So first of all, you have to find the poles. That is equate denominator is equal to 0, so you will get 2 poles plus minus 2. Minus 2 lies outside this closed curve, so we'll neglect it. And plus 2 lies somewhere inside this curve. So the integral by Cauchy residue theorem is simply two pi I times one more thing which I would like to say that there is plus minus 2 pi I. It is very important. Plus when the contour integral is going in the clockwise direction, in the anti-clockwise direction, this. Oh, sorry. So yeah, when we have anti-clockwise direction, then you have to take plus sign, and we have clockwise direction, then in that case you have to take minus sign. So that keep in mind. When you have this is clockwise, so minus sign, and when you have anti-clockwise contour, in that case you have to take plus sign. In general, if in question they have not mentioned anything, then you will assume that the contour is taken along the counterclockwise direction. So plus. So here there's nothing mentioned in the question, so we'll take that this integral is taking anti-clockwise direction. So we'll have plus 2 pi I times the sum of residues at the poles which lie within this closed curve. So there is only one pole which lie within this contour C, which is at z is equal to 2. So your integral will be nothing but 2 pi I times. And you know, in the last class we know that how to calculate the residues for a simple pole. Z minus 2 times Fz, which is Fz cube plus 3z square, Z minus 2, Z plus 2. This is cancelled. So it is 2 pi I times. Just put 2 in this, so you get 40 plus 12 upon 4. So this is 52 by
16 pi
4.
I.
Huh?
16 pi iota आंसर आ रहा सर.
26 pi iota. Not 16. 12 divided by 4. So it is 26 pi iota, and when you will just multiply it, because in the question they ask usually up to 2 decimal places. 2 decimal places. So it will become some like 81.64 iota. They've asked absolute value, so you'll write 81.64. Like you're not worry about this imaginary. You just write 81.64. So that will be the answer for this question. Is it okay?
सर ये क्वेश्चन मतलब कॉस्ट इंटीग्रल फॉर्मूला से भी सॉल्व हो सकता था.
हाँ, that could have been solved. क्या बोले आप?
सर कॉस्ट इंटीग्रल फॉर्मूला का यूज करके भी सॉल्व कर सकते थे इस क्वेश्चन को.
हाँ, डिफरेंट वेज है सॉल्व करने के, लेकिन क्योंकि ये कॉम्प्लेक्स एनालिसिस के अंदर है तो डायरेक्टली कॉची रेसिड्यू थ्योरम से भी हो सकता है. If you have solved this using some separate method, that's good only. Okay, so is it clear this question? So I'll move to next
Yes,
question.
sir.
So this is another question where simple same you have to find poles. Like first you will just find the poles. You have to just find the contour integral. This will evaluated along a contour going from minus infinity to infinity along the real axis. So you have to first draw the curve. So they are saying that this closed curve is going from minus infinity. Suppose this is minus infinity for the sake of clarity. So it is going from minus infinity to plus infinity somewhere here. And then it's the real axis. We all know that it's the real axis. And then it's closed in the lower half plane. That is, lower half plane is this by a half circle. So it's something like this. So your contour is going in, remember this contour is going in clockwise direction, because in the question they have mentioned this direction. It's going from minus infinity to plus infinity. Therefore, in this case, while doing the integral, you will have minus sign in the front of. So as usual, you will first find the poles. So it is 1 plus z square is equal to 0. So z square is equal to minus 1. So your poles will be plus minus iota. Plus iota is lying outside this curve, so we'll neglect it, and only a minus iota will be taken into consideration while doing the integral. So by Cauchy's residue theorem, this is nothing but minus 2 pi, minus because this contour is going in the clockwise direction. Therefore, minus 2 pi I times residue of that function fz at the poles which lies within this curve C. So this is z is equal to minus. So it will be minus 2 pi I z plus iota 1 upon z plus iota z minus iota at z is equal to minus iota. So this will cancel out. So it will be minus 2 pi I times. Just put, so it will become 1 upon minus 2 iota. So minus 2 iota cancel, it will pi. So your answer will be, since you have been asked to provide the answer to 2 decimal places, it will be 3.14. So simple procedure: first find poles, then see which of the poles is lying within the curve, and then just use this Cauchy residue theorem to find the answer. And also be aware that in the question, if they mention that the contour is going in the clockwise direction, then you have to take minus sign. So this is clear?
Yes, sir.
Okay. Now this question I would ask you people to solve, like it's simple only. So this also you have to first find the poles. First of all, just draw the diagram. So the circle is centered at 0. Z minus 0 is equal to 3. Its radius is 3. So it will be somewhere like this. Okay. Its radius is 3. So you have to find poles. So simple. It has pole at z is equal to -1 and the order of pole is 4. Okay, so the pole is lying at z is equal to -1 in order of pole. So by using Cauchy residue theorem, your answer will be 2 pi I. In the question, they have not mentioned the direction of the contour, so you'll take it counterclockwise direction. This, so plus 2 pi I times residue of fz at z is equal to -1. Now, in the last class, I told you that how to find residues of a function for when a pole is of order n, when we have a pole of order n, which here the order of the pole is 4. So it will be 2 pi I times 1 upon 4 minus 1 factorial dm minus 1, so d3 by dz cube of the z plus 1 to the power 4 function e to the power 2z upon 1 plus z to the power 4 at z is equal to -1 because of the radius is 3. So you just, when you solve this, so it will come out 2 pi I times 3 factorial, which is 6, and this is cancel out. So 3 times when you differentiate, differential of exponential will give exponential, so it will be 8 times exponential 2z, z is equal to -1. So it will be nothing but 2 pi I times 8 by 6 into e to the power -2. So if I simplify it, it will be 8 pi iota by 3 exponential -2. So option A is the right answer. So this simple application of first to find the poles, then you just use Cauchy residue theorem to find the answer. Is this clear? Hello?
Yes, sir.
Yeah. Now, suppose you have got a different kind of question where they have not asked in this question to find the contour integral. They have just asked you that what singular points or what the poles will contribute to this integral. So in this case, you have to just find the poles. So the poles is z to the power 4 plus a to the power 4 is equal to 0. So z to the power 4 is equal to minus. Now what you will do, so generally when you get this kind of high order poles, then you just, -1 can be written as cos of 2n plus 1 pi plus iota times sine 2n plus 1 pi, where n is 0, 1, 2 up to infinity. So if you put n is equal to 0, you will get just get cos pi, which is -1. So, and this term is always 0 because it is integral multiple of 2 pi. So, and we know that sine 2 pi, 4 pi, 6 pi, those all are 0. So we can write this, and we also know that we can express cos and sines in terms of exponential like this. So we can write this equation, suppose this is equation 1, as a to the power 4 exponential iota 2n plus 1 pi. Okay, you can easily write this as this. Now it is easier to do, you just take 1 to the power 4 on both sides, so it will become a times exponential iota 2n plus 1 pi by 4. So you got the poles. The poles of this function fz is at these points where n is 0, 1, 2, 3. Now you again write this in terms of cos and pi's, because it is easier to put the values of cos and pi, and then we can easily find that cos 3 pi by 4 is what. So you can write this as cos 2n plus 1 pi by 4 plus iota sine 2n plus 1 pi by 4. Okay. Now you just put different values of n. For example, if you put n is equal to 0, then you will get a times cos of pi by 4. Cos of pi by 4 is 1 by root 2 plus iota sine of pi by 4, which is also root 2, which you can write as a by root 2 1 plus iota. Now put n is equal to 1. Then you will get, suppose you say z1, z2. You will get cos of 3 pi by 4, and the cos 3 pi by 4 is what? If you'll just solve it, you will come out, it will be minus 1 by root 2, I think. And sine 3 pi by 4 is plus 1 by root 2. So you can write this minus 1 plus iota. For n is equal to 2, if you put, you will get both minus. So minus 1 by 2 minus iota by root 2. So minus a by root 2, 1 plus iota. And for n is equal to 3, your value is 2 3s are 6 plus 1, 7 pi by 4. So 7 pi by 4 is what? 1 by root 2 minus iota by root 2. So it will be 8 by root 2, 1 minus iota. Now when you put n is equal to 4, as soon as you put n is equal to 4, your value will become 2 4s are 8 plus 9 pi by 4. This 9 pi by 4 is greater than 2 pi. So the cycle will repeat itself. So again, when you put n is equal to 4, you will get this value. You will put n is equal to 5, you will get this value. Because sines and cosines have a cycle periodicity of 2 pi. So you just stop at this point. And these 4 points will contribute to this integral. And also that these will lie within this radius 2a, because you will just calculate this 1 by a by root 2 term is coming, 1 by root 2, 1 by root 2, so they are less than 2. So these 4 poles will contribute to this integral. So out of these 4 options, option D is correct. So in this way, whenever you get this kind of questions where you have z to the power 4, then you can just use this kind of approach to find the poles. So, any doubt in this question?
No, sir.
Main point is where to stop. So you know that you have to stop after n is equal to 3. After n is equal to 4, you will get this value. N is equal to 5, you will get this. So it is a cycle. Now another question which came in GATE 2021. I hope you must have solved it. But the question is that there is a contour integral in this dz upon z minus n the whole square plus pi square, where n is some positive integer, and c is the closed contour as given in this diagram. It is going in the anti-clockwise direction, and the domain is minus 100 to plus 100 in the real axis, and it is a semicircle in the upper half plane, positive plane. So what is the value of this integral? So summation n is equal to 1 to 5 I times n. So first of all, you have to find the poles. This kind of question, the first step is to find the poles. So for this question, your poles will be what? Z minus n is equal to plus minus iota pi. So z is equal to n plus minus iota pi. So these are the poles. Now find what are the poles which lies within this closed curve. Now I pi will lie somewhere here and minus. So you know that since this minus term, this minus imaginary number, this minus iota pi lies outside this closed curve, so we'll neglect n minus iota pi, and the only poles which will contribute to this integral will be z is equal to n plus iota pi, because minus I pi is outside this domain of this closed curve. So these are the poles where n is what? N is ranging from 1 to 3, 4 up to whatever number. In this question, now you just find this in by using simple Cauchy-Residue theorem, which is 2 pi iota times. Maybe I will use another page. So by Cauchy-Residue theorem, your in will be what? 2 pi I times the residue of the function fz at the poles which lie within this closed curve. So here it's n plus iota. Now, just z minus n minus I pi times fz, which is, you can write this as 1 upon z minus n minus I pi z minus n plus iota pi. Because I have factorized this, because you know that it has two roots, n plus iota pi and n minus iota pi. So this denominator can be written as z minus of this times z minus n plus. When you just multiply this, you'll get this only. So just another, okay. It's like, yeah. So this will cancel out, and your in will be what? 2 pi I times. You'll just put the value of z, which is n plus iota pi minus n plus iota pi, and then cancel. So it will be 2 pi I times 1 upon 2 pi I, which is 1. So your in is 1. So in the question they have asked, what is the value of? So just you have to find I1 plus I2 plus I3 plus I4 plus I5, like 5 times. So it will be just 5, 1 plus 1 plus 1 plus 1. So, and suppose in the question, if the domain was, suppose instead of minus 100 to 100, if the domain was suppose minus 4 to 4, then in that case only n is equal to 1 to n is equal to 4 would contribute to this integral. N is equal to 5 would have become 0, because n is equal to 5 lies outside this closed curve. So you have to take in, but since the domain is here 100 to minus 100, where n can range from 100 to minus 100, so all these values from n is equal to 1 to n is equal to 5 will contribute to this integral. So is this clear?
So
Yeah. So
Sir, if we have n equal to 4
hmm,
and it is z is lying in 4 plus I pi, no? So it will lie outside the curve. So we won't consider it, no?
if z is equal to, if n is equal to 4,
Then z will be 4 plus I pi, no?
yes, then 4 is somewhere here, right? It will lie somewhere here, 4 plus iota pi, because iota pi is here, 4 is here, which is within this closed curve.
No, sir, for the case of I was saying.
Yeah, for in the case of 5 also, it will lie within curve only. So we'll take I is equal to 4, we'll neglect I is equal to 5, sorry, we'll neglect I is equal to 5.
No, sir, we will neglect I equal to 4 also, right?
Why? I is equal to 4?
Sir, it will lie
Okay,
directly
okay.
outside the curve,
Okay,
no?
okay. No, no, actually, suppose if this is from minus 5 to 5, then you will take up to 4 and you neglect 5, yes. Now is it clear, right?
यस सर सही कह रहा है क्योंकि इसकी जो रेडियस है वो इस पॉइंट की जो रेडियस है वो 5.08 हो जाएगी जो कि आउटसाइड है.
हाँ राइट. Yeah, so my point was, yeah, I was also saying the same thing that since here the limit is very large, so we can take all the points n is equal to 1 to 5 into the integral. This is clear, right?
यस सर.
Hmm. Now, this is the last question for this part, like complex analysis. So here they have asked you to find this integral minus infinity to cos of kx upon x square plus a square dx. Okay, where k is greater than 0 and a is greater than 0. So this type of question, when you see, when you have this kind of integral, then you just you can write it at as the real part of, because you know that real part of this is what, cos of kx plus I of sine kx. So cos of kx by x square plus b square dx is nothing but real part of exponential I kx upon x square plus a square dx. So now you find the poles. So the pole says x square plus 0. So x square is equal to minus a square. X is equal to plus minus. So these two are the poles. So when you find this kind of integral, then what you do is that you construct a semicircle in the positive side. Okay. From minus radius of this circle is 1. And in generally, if you have any integrals, contour integral C, so you can split it into two parts. First is integral along this real axis, and the second is a integral along this semicircular curve. This. Okay. Now, if you just assume, because in our case the limit is minus infinity to infinity, you just put the radius tends to infinity, the radius of the circle tends to infinity, then in that case we can write, in our case the function is what? Fz is nothing but exponential I kx upon x square plus a square.
Is the answer A?
Yes, is right. Answer is A. So exponential I kx upon x square plus a square dx. I'm just writing this only, but just replacing the fz with this function and replacing the limits with infinity to minus infinity to plus infinity. Now, there is one theorem which can be used here. This is when we know that limit is, this radius is tending to infinity. So at limit r tending to infinity, just we know that we can write this as this, because from the diagram itself, the radius is r, so exponential is what? R cos theta. So we can write this as r exponential I theta, and where r is the radius and this is the phase. This is the phase and this is the amplitude, and hence dx is nothing but r I exponential ei theta d theta. So when you just replace these things, so it will become something e I k x will become r exponential I theta, dx will become iota r exponential I theta d theta, upon a square plus x square, which is r square exponential 2i theta. Now, and this integral, limit will be 0 to pi because we are integrating along this semicircle. So this integral by Lemma Jordan rule for r tending to infinity, it tends to 0. So you are interested in finding this integral. So that is nothing but if you are able to find the contour integral of this function, that will give this. And we know that how to find this contour integral using Cauchy residue theorem. So your minus infinity to infinity exponential I kx x square plus a square dx will be nothing but contour integral of this. And this you know how to solve. You first find the poles. The poles will be uh, plus minus a iota, and you know that minus a iota lies outside this outside this curve. So only plus iota will be contributing. Minus iota will not contribute to this integral. So you can just simply write it as 2 pi iota times by using Cauchy residue theorem. X minus ai e to the power I kx x minus ai x plus ai limit x tending to a. This will cancel. So it will become 2 pi I times exponential I k a times iota divided by 2ai. So 2i cancel. So it will become pi by a exponential iota square is minus, so minus k. Okay, so your integral minus infinity to infinity exponential I kx x square plus a square dx is this. And in the question they have asked this, so cos is nothing but the real part of this integral. And we know that this imaginary part is 0. So your integral cos of kx upon x square plus a square dx is this only real part of this integral, which is. So as someone already said that question option number A is the right answer.
सर
Hello.
सर इसमें जो इंटीग्रेशन के दो पार्ट्स हुए हैं तो एक इंटीग्रेशन टेंस टू जीरो हुआ है, वो अलोंग कर्व था क्या?
हाँ वो लॉन्ग कर्व था.
ओके सर.
सर ये तो क्वेश्चन है कि ये जॉर्डन लेने का जो रूल है कि अलोंग कर्व इंटीग्रेशन 0 होता है, इसके लेमे जॉर्डन रूल इसके मतलब इसे कब कब हम अप्लाई कर सकते हैं, इसका कोई बता पाएगा लेमे जॉर्डन रूल के बारे में, क्योंकि इससे ज्यादातर कर्व के इंटीग्रेशन को 0 कर दिए देते हैं.
So you want to know go into detail that why this Lemma Jordan rules. So that is actually a derivation for that and little lengthy. So since there is some limitation in time, won't be able to go in today's class. So, but if you want, I can. If there is some classes after next week, then I will cover the extra things because right now I'm trying to finish all the questions for Fourier transform.
I can use this rule to take the integration along curve 0 for any this kind of integration where they have asked me. Okay.
Yes. You can do this simple approximation.
Okay.
You just remember, yeah. Okay. Okay. So so basically I've covered all the questions which have been in GATE exam. So this type of questions you usually get, and now I will start Fourier series. And okay.
सर मैंने 2 क्वेश्चन मेल किए थे आपको कॉम्प्लेक्स रिलेटेड.
हाँ you mailed me. So okay, so since I have some time and I can, maybe I will just do that also. Okay, so one question was sent by one of the student, Harish. So two questions actually. So I think since it would be helpful. So they have this kind of integral was asked, right? Along some unit circle, along some unit circle. यही पूछा था मैं. Hello.
Yes, sir. Yes, sir.
So yeah, so first of all, you can write this in this in form cos z dz and find the poles. So cos z is 0. So z is what? 2n plus 1 pi by 2, because you know that cos is 0 n, like it is 0, it is pi by 2, so 2 pi, 3 pi by 2. Okay, so in all the 5 pi by 2, so all the integral multiple of like, so for all these values, your cos is 0. Okay, so
Sir,
hello.
sir, can we
Sorry,
do it
sorry,
like
sorry.
Yes, sir.
Sorry. Hello.
yes? Can we do it like this, that we
Sir.
can write cos z as z plus 1 by z, and then just find the poles for z?
Hmm.
Can we do it like that also?
What? Fine.
We can write cos z as z plus 1 by z, 2 by z plus 1 by z, and then we can try to find the poles of that z square plus 1.
Okay, yeah. If you have used that method, yeah, that could be used. But this is direct. No, why to use complex? Like you can
Oh yes,
directly.
yes, because here cos z is 0. So
Yes. So here you can directly. You know that here it will be 0. So your poles are lying. I think the question they have asked two things. What is this integral I? And second, what are the singularities? So your singularities will be simple. This z is equal to 2n plus 1 pi by 2, where n is 0, 1, 2. And your integral, since they have asked you to do this along some unit circle curve, unit circle means the radius of the curve is 1, radius of the circle is 1. And the small, if you take n is equal to 0, in that case your pole is pi by 2, which is greater than 1. So it is like, so even the lowest order pole is lying outside this unit circle curve. So all these singularities lies outside this curve. So your integral will be 0. So this is the answer. Harish?
Yes, sir. And what about singularity?
Singularity is these poles. Poles are singularities. 2 and plus 1.
Sir, in a question, the singularity set equal to 5 दे रखा.
There must be some, I think, but I think this is the only right answer. I is equal to 0 and 2 and plus 1 pi by 2. Okay. Because it is straightforward, right?
Yes, sir. But singularity 5 दे रखा, पता नहीं.
It must be printing or some typo error, I think.
Okay, I can verify.
Yes, you can verify. And then there is another question is that there is some function f of z, complex function in this form. Then they've asked what is the contour integral 1 plus fz by z, right?
Yes, sir.
So here you just put uh, fz is equal to c naught plus c1 by z dz. So you can write this as z plus c naught z plus c1 upon z square. Now poles is what? Poles are what? Z square is equal to 0. So pole is at 0, but the order is 2 because it is Z square. So your residue will be, so you're using Cauchy residue theorem, this integral 1 plus fz by z dz will be 2 pi I times 1 upon 2 minus 1 factorial, which is 1 factorial, d of m minus 1, that is 2 minus 1, so d of dz of this function, which is, sorry, z minus 0 whole square up into z plus c naught z plus c1 upon z square at z is equal to 0. This is cancel out, so you have 2 pi I times, just differentiate this, so it will be 1 plus c naught, z is equal to 0. So there is no z term, so the answer will be this, 2 pi iota 1 plus c naught. Okay.
Yes, sir, clear.
Oh yes. So this time questions are like you just have to find the poles and then just use Cauchy residue theorem to find the answer. Okay, so we have solved enough questions today on the complex analysis. So I will just today's class might extend for 5-10 minutes. So I hope it's okay with you all. So Fourier series also is an important part, but it is not as important as complex or differential equation or Fourier transform like this, but questions comes from Fourier series also some. So to start with, what is Fourier series? So Fourier series, I will not, like in the last lecture, phase 1, I just gave some introduction of what is Fourier series and all. So those things due to time limitation I won't be doing. But, simply if you want to represent any periodic signal, can be represented by or approximated is more appropriate, by linear combination of sines and cosines. Okay, you might take infinite linear combination of sines and cosines to represent any kind of periodic signal. So suppose you have any signal, any function fx or any signal fx. So in the mathematical form, it can be written as this. You all must be knowing this. Plus so this is how you represent any signal fx, any function fx which is periodic can be expanded in this form, this Fourier series expansion form, where an and bn are the Fourier coefficients and L is the half period of the function. Half period of the function. Now, another important thing is you have to evaluate this coefficient. So how to evaluate this coefficient? So suppose you want to evaluate A naught. So there is a direct formula that A naught is 1 by some 2L minus L2L fx dx. So how you do it? So simply is that you integrate both sides from minus L to L dx. Okay. So when you integrate both sides, then this term, or suppose your L is nothing but L is pi, it will be much clearer. It is pi periodic. So suppose you have suppose your L is pi, so your above that becomes what? And you integrate this equation 1 from minus pi to pi, a naught minus pi to pi dx. Similarly, you integrate this also from minus pi to pi dx, and this term also. Now, these term cos and sines, when you integrate from minus pi to pi, they will just vanish because you just can try because they are periodic. So it limits is, so when you evaluate this integral, so cos of n pi x by l and these two terms will just vanish out. So what you will left with is, this will be something like a naught 2 pi, and here you will be have minus pi to pi fx dx. So that essentially is that a naught is what, 1 by 2 pi minus pi to pi fx dx. So here how you get this coefficients. So similarly you can calculate an and bn also. So I will just write these coefficients. So a naught is 1 by 2 pi, or in general form L, let is pi by L, so minus L to L fx dx. This generally represents some area. We know this integral represents some area under the curve, minus L to L. Okay. So, and an is simply 1 by L minus L to L fx cos of n pi x by L dx, and bn is 1 by L fx. So this is general way of three coefficients a naught, a and bn of this Fourier coefficients. So suppose a question which came in gate. Okay, so yeah, so there is a question which came in gate 2016. So they have given some periodic function fx of period 2 pi, and it is defined in this interval minus pi to plus pi. So the function is this. It is minus 1 to 1. So first of all, you just plot this function minus 1 to 1. So this function is from the limit minus pi to 0, it is minus 1. So suppose minus 1. So from minus pi to 0, it is minus 1. And then from 0 to pi, it is becoming 1. So you can see that this function is kind of anti-symmetric about the origin. So fx6, or you say it is anti-symmetric about the origin. Or you also say that it is an odd function, those kind of things. So if you find this integral a naught, which is what? So here you just replace, first of all, what you will do is that in this formula, you will just replace L with pi. So your a naught will become 1 upon 2 pi integration minus pi to pi fx dx. So 1 upon 2 pi minus pi to pi fx dx. Now you can just calculate this integral, because you know that from minus pi to 0 it is minus 1, so minus of dx plus 0 to pi to dx. So when we calculate this, it will come out to be 0. Or in short, if you want to remember, because this fx is what, this area, so this area is exactly opposite to this area, so this will cancel out, so a naught will equal to 0. Similarly, when you calculate an is what, 1 by pi minus pi to pi from this fx cos, you just put L is equal to pi, so pi will cancel, so it will become cos of nx. So fx cos. Now you know this function fx is antisymmetric about the origin, and cos, or you say another word is odd. So fx is odd, the odd function, and similarly cos of nx, cos function is also what? Cos function is symmetric about the origin, because you know the cos function is something like this. This is how cos function looks like. Cos function is symmetric about this origin. So it is even. So cos function is even, fx is odd. So odd cross even will become odd, and hence this integral from minus pi to plus pi will be 0. So what I mean is that whenever you get an even, whenever you get an odd function or this kind of antisymmetric function, in that case, the coefficient a naught is equal to 0 and an is also equal to 0. And bn, what about bn? Bn is 1 upon pi minus pi to pi fx sine nx dx. Now sine function is what? Sine function is also antisymmetric about the origin. Okay, so sine function is also odd. Your so odd. So odd becomes even. So this function bn coefficient will not be equal to 0. So in this way, directly if you just, because you have some limitation of time, so directly you can say that option A, C and D will not be there because A naught and An is 0. So A naught and An is 0. So this and these two terms will vanish. So whatever is left is just, sorry, this will be sine, my mistake. So whatever is left is sine terms. So you have to just find directly bn. No need to find a naught and b an. Just find directly bn. So bn is what? 1 by pi. From minus pi to 0 it is minus 1. So minus of sine of nx dx. Is this clear what I'm saying? Hello?
Yes, sir, clear.
Hmm. Now we just do this integral. It is a simple integral, so it will be something like this. So integral of sine of nx will be what? Minus minus cancel, so it will be 1 by, sorry, it is, yeah, 1 by n cos of nx, 0 to minus pi. This will be minus of 1 by n cos of nx, pi to 0. Now just put the value of the limits, so it will become, take n common from both. So it will become cos of 0, which is 1, minus of cos of n pi. And this will become minus of cos of n pi. And cos of 0 is 1, minus minus plus, so it will become plus. So it will become 1 upon n pi, 2 minus 2 cos of n pi, or take 2 common, so 2 by n pi, 1 minus cos of n pi. Now cos of n pi, how you can write? So you can easily, you know that cos of n pi is equal to 1 for even n. For n is equal to 0 or n is equal to 2 or 4, it will be 1, and it is minus 1 for odd n. So you can write bn as 2 by n pi 1 minus 1 to the power. You can easily write cos n pi as this. So that for even n, it will, what it will become? So your bn will become, for even n, it will be 1. So 1 minus 1, 0. So it will be 0. For odd n, your cos of n pi is minus 1. So 1 minus of minus 1 is 2. So 2 times 2, that is 4 by n pi. So this is your coefficient. So your fx is nothing but a naught is 0, and all the an terms will, an coefficients are also 0. So only left with bn sine of nx. Okay, so and you also know that for even n will be 0, so only odd terms will come. So what will come? B1. B1 will be what? B1 will be 4 by pi sine pi. Similarly, n is equal to 3 when you put, so you'll get, I've taken 4 by pi common, so 1 by 3 times sine of 3 pi. Similarly, 1 by 5 sine of 5 pi up to infinity. So only these terms will be there in the coefficient Fourier series expansion. So out option A, 4 by pi sine x plus sine 3x by 3 plus sine 5x by. So you no need to find all the coefficient. First of all, see what kind of function it is. If it is odd function, then you can just calculate Bn. And if it is even function, so for odd function or antisymmetric function, A naught and An will be 0, Bn will be non-zero. For even function, your A naught and An will be not equal to 0 and Bn will be 0. Remember this, okay? Now another question. However, in the question it is written that the question is that find the coefficient of exponential ikx in the Fourier expansion of this function. So don't. So this kind of question is a little tricky. You no need to. You don't actually need to know Fourier series. You can just directly solve this. How to solve is that you can write this as. Now you know sine of ax can be written as exponential iota ax minus exponential minus iota ax upon 2i. So you just substitute this. So upon 2i whole square. Okay, you can write this sine ax. Now just take this things outside, so it will become minus a by 4. And you just apply this formula a square minus b square, so it will become minus 2 times. Okay, so this is now in the question they have asked the coefficient of exponential ikx for k is equal to minus 2a. So put k is equal to minus 2a here. So it will be what? E to the power minus iota 2ax. So they have asked the coefficient of exponential minus 2x. So in this question, the coefficient of exponential minus 2x what? Minus a by 4. So directly you can find this question. So little tricky. So no need to just expand this in this form and just easily find this coefficient. Or other ways was you have to find the coefficients like complex Fourier analysis, which is not required here. So just simple approach, you could have find the answer. What I'm telling is that suppose in other approach was you have to find this coefficient as this, some 1 by 2 pi fx exponential I kx dx. Using this formula where your fx is what, this a sine square ax. So a sine square ax exponential ikx. Now here you substitute sine ax as this, and then you solve this integral, then you'll get some. So that will become little lengthy. So you could have easily solved this using this approach. Is this clear, this question?
Yes, sir.
Yes, sir.
Now another question in GATE 2019 it came. It was they're given some function psi of theta which is 1 between minus pi by 2 and pi by 2, and it's 0 otherwise. So if its Fourier series is written as in this form, so psi of theta is summation m minus infinity to infinity cm. So this is nothing but Fourier series in X complex form, complex notation. Okay, so they have already given in the question. Then what is the value of C absolute C3 square whole square, absolute value of C3 whole square? So remember this formula, this Fourier coefficient in complex notation can be written as 1 by 2 pi, the limits which are given minus pi to pi, psi of theta exponential e. Okay, so you just find this, because you just find this coefficient using this formula, so it will become cm will be what, 1 by 2 pi. Now your function is defined only within these two limits, minus pi by 2 to pi by 2. So it is 1. So xi theta is 1. So 1 times exponential im theta. Plus for all of the limits it is 0. Outside this domain pi by 2 minus pi by 2 it is 0. So 0 times this will become 0. Now this is integral which is easily you can find. It is exponential im theta upon im. So your cm is what? 1 upon 2 pi im, and just put the limits. Just put the limits pi by in place of theta, so you will get exponential im pi by 2. Now that's simple that you can just write this as what? 2i times sine of m pi by 2. You can write this, right? Because sine of theta is e to the power I theta plus minus e to the power minus I theta by 2i. So, and then this will cancel out. So you'll have sine of m pi by 2 times m pi. So this is general for any coefficient. For different values of m, you can get different values of these coefficients. In the question, they have asked C3. So m is equal to 3. So it will become sine of 3 pi by 2 divided by 3 pi. Now sine of 3 pi by 2 is what? This is pi. This is pi. This is pi by 2. This is 3 pi by 2 is minus 1. So it is minus 1 upon 3 pi. So this will become square of it. And I think it is something around 0.011. Because in the question they have asked up to 3 decimal places. So you just use simple this formula to find the coefficient C3. Okay. Clear this question?
Yes, sir.
Okay. Now two more questions. I think 2 or 1 maybe, or maybe, yeah, only one question. So yeah, this is another question where they have given some function fnx which is 0. So let us draw. So there is some function fnx which is just defined between these two limits, minus 1 upon 2n, 1 upon 2n. So within these two limits, your value is n, and outside these limits, the value of this function is 0. So they have asked what is the value of this integral. So this is a little tricky question. Like it's easy, but you have to just apply some brain. So limit n tending to infinity. So when n will tend to infinity, or when n will become large, what will happen these two limits? Any guess? What will happen these two limits? Will it go outside or inside when n will become large?
I guess if n tends to infinity, this will behave in something like a delta function because
Uh, yes, yes, correct, right. So yes, he said right. So when n will become large, then this 1 by 2n will become small and small. So in the limit n tending to infinity, this limits will go towards the center origin, and similarly your this function n will become very large. So this function will transform in limit n tending to infinity. It will assume a delta function say, which is centered at around some 0. Okay, some delta function which is centered at 0, because area is conserved. So this thing is getting inside. So this function will become n will tend to infinity. Okay, so your limit n tending to infinity fnx is nothing but delta function. So in this question, you can just replace this in this form. And then there is one property of delta function that delta x minus a, suppose there is some x1 to x2, fx dx is f of a when your a is within these two limits x1. So here also your function is what? Minus infinity and infinity delta x minus 0 sine of x dx. So this will become what? F of a or sine of a is 0, so sine of 0, so it will become 0. So the answer of this question is 0.
Sir, the given function in the question is a symmetric function. So can we not say that then fx sin nx should be 0 as the function is somewhat symmetric along y-axis? So the odd terms, when integrating for the odd term, this integral will become odd.
Yeah, yeah.
So
Yes. Since it is even, so and since cos is also even, so this symmetric. Yeah. So
so the
yeah,
integral should be odd one.
yeah. So this is kind of coefficient only. So you're saying that.
Yes, I'm just saying that the function is even and sine is an odd function, so the integral is as a whole is odd. So when I'm
Yes.
integrating from minus infinity to infinity, it will become 0.
Yeah. That's another approach. Yes. Correct. Right. Mhm. So everybody understood what he was saying. He was just saying that simple whatever we were telling in Fourier series, that since this function is even and sine is odd, so even odd is odd. So in these limits, it will just vanish. This integral from minus infinity to infinity will just vanish. Okay, so this question you can just tell me answer right now. It is easy. I just told you. Some function is there which is symmetric, periodic. Then in general, the Fourier series expansion will be a block form.
B, I guess, because only the symmetric part will survive.
Mm-hmm. Yes.
D option, sir.
Okay. Okay, so yeah, that is what I have to cover in Fourier series and complex analysis. In the next class, I don't know whether next class is going to be last class, but they told me in the starting that we'll have 10 lectures. So today was 9th, so next week we'll have 10th lecture. So
Are you
I
going
will
to
cover.
cover Laplace transform in the next class?
Hmm?
Will you cover Laplace transform by any chance in the next class?
Yeah. In next class, I will be doing Laplace and Fourier.